अरे यार। Okay, so no one is joining, so we'll start after 5 minutes. If no one join, I will just play the video and recording the session. Hi everyone. Now we discuss about one question. Hi everyone. Hi Ankit. Are you able to see the question? Hi everyone. Now we will solve the one question from GATE 2019, question number 4. So first read the question and try to tell me what will be the answer A, B, C, D. So anyone can tell me the answer? It is the Peterson elimination name reaction. It's many times came in the GATE and NET. So okay. As is staying option B. So any other option? It's very easy question actually. Okay, let's solve them. Hi everyone. Now we discuss about one question from GATE 2018, question number 4. The major product of the following reaction is, so this is our substrate where silyl methyl group is there, one OH group is there, and in their particular stereochemistry, and we are treated with potassium hydride. And there is a code option. The first option is the formation of the olefin with trans in stereochemistry, and option B is the formation of olefin again with cis stereochemistry. Option 3 is the formation of epoxide, and option D is the substituted silylated compound. So we have to find out which option is correct. So this is the name reaction which is known as Peterson elimination. So so there is two conditions where the Peterson elimination is happen. One is acidic condition and another is basic condition. In acidic condition, basically equitable elimination is happen with anti-peripheral type transition state, but in this particular case, there will be a thin peripheral geometry, and the reaction will happen like E1, not E1, like thin peripheral geometry. Okay, so for that, so we have to read the restructure like this. So we are basically redrawing the structure like this. So the R group is in this side and this H in this side and this SMI3 in group in this side. Similarly, these two R group in it basically in different side because see this is the zigzag form, right? We are basically presenting this bond like this here and this R and R group in different side. So here the R is basically CH2, CH2, CH3. So we can, so this reaction will happen basically from thin plate planar geometry. That's why we have to make the silicon center and the oxygen center in the same plane. So for that, we have to rotate this bond every this bond like clockwise direction 60 degree, 60 degree in clockwise direction, clockwise direction. So then we'll get this particular form. And if we rotate this bond in anti-clockwise direction like this, and again 60 degree, then we'll get this thing. So at the when we treated with potassium hydride A plus H minus, this H minus will abstract this proton, and there will be a possibility of formation of Si Me3 O minus R group this side, H this side, H this side, R this side. So it will come here. So this oxygen lone negative charge will attach to the vacant d orbital of the silicon. And one thing is that always remember the silicon always try to attach with electronegative atom. So silicon has a great affinity towards the electronegative atom because that type of bond is most stable bond. So we'll get the structure like this. So transistor should be like this: Si Me3 minus oxygen, here H, here R, here H, here R. This H and H will be in the same side. Okay. So after that there will be a like bond break will like happen like this. So we'll get a stereochemistry like R group in the same side. So our product will be the cis product with same stereo with cis olefin. Okay. So the correct answer will be option B, and option A is not correct option. And this type of epoxide formation is not possible because for that oxygen center group will be attacked here and SiMe3 group have to leave. But the SiMe3 group is a not good living group. That's why option C is also not good. And option D, for that this hydrogen should be abstract and this lone pair will come here and this OH should be leave. But that type of oxygen OH minus is also not a good living group, and this hydrogen is also not acidic in nature. That's why the option D is also not correct. So the correct option will be option B. So for more this type of video, you can watch this NPTEL video. Thank you. Okay. So at the when we treated with, can you tell me the when if we treat with this with acid, what will be the product? Like H plus and water. If the same reaction treated with H plus and water, what will be the product? So that time the stereochemistry will be in transparent. This is thin peripheral geometry because thin peripheral means SiMe3 and OH in the same side. But that time SiMe3 and OH would be in different side. I mean 180-degree angle to each other. Okay, that's why I call anti-peripheral geometry, and this is thin peripheral geometry because the angle is 0 degree, dihedral angle. So any guess, any answer? So let's say SiMe3, here H, here R. We have to rotate this bond, so OH will come this side and H this side and R this side. Now tell, sorry, just rotation. Now tell me, what will be the pseudochemistry? Cis or trans? If the reaction is happening like protonation here, H2O plus and water just attack like this. Now what product will get? Cis or trans? Get trans, right? So in acidic medium, we will get trans product, but in basic medium, we will get cis product. So this reaction comes every alternative year, I think. So remember this question. It's a very good question. So now we play another video. Hi
Hi
everyone.
everyone.
It is relatively hard question. So take time and solve first. First read, then solve. Okay, so basically we are taking one substrate, right? We are taking one substrate and now we
Now we
discuss about, so we are taking one substrate and we are treating with organolithium compound. See, CH2 has CH2 minus, that CH minus and Li plus. So we are treating with organolithium compound. Can you tell me where this organolithium compound will be attacked and what are the possible site of attack? Possible. One attack is possible in the keto, another site in double bond, normally not preferred, another is 1,4 addition, right? So where it will attack? In the keto position or unsaturated double bond, like methyl center, where the methyl is attached. So can you tell me organolithium is a hard compound or soft compound? I mean hard interaction is there or soft interaction is there? I mean or lithium compound is hard in nature or soft in nature? Good, good. Keto, yes, that will attack to the keto site because this is hard in nature. Okay, so that will attack to the keto center. So not the alpha beta unsaturated ketone because there is the soft center. So we'll discuss this and then we'll
one
solve.
question from GATE 2020, question number 30. So the major product formed in the following synthesis sequence is, so first this is our substrate. First we reaction with organolithium compound followed by THF 78 degrees centigrade, and next step is the potassium hydride which is 25 degrees centigrade THF, and we are using 18.6, that is round third. So let's see our substrate. Okay. So in our substrate also 1, 2, 3, 4, 4 center is there, right? This is alpha beta unsaturated compound and here is the isolated double bond. So our lithium, so where will we attack? Will attack whether this 2 center or 4 center. I mean that is we have to find and followed by the conjugative reaction. So there is a fourth option. In one option, this particular bond, this methyl and this CH2 in the same side, but in this option, this methyl group and CH2 in defined side. This methyl group and CH2 in defined side, and in another case, this methyl group and CH2 in same side. And in one option, there is the ring is get aromaticity, and the fourth option, the all other things are basically break. So you have to find the correct answer. So the reaction is basically one name reaction, that is the oxycove rearrangement, in which there will be the one OH group there will be there, and at the high temperature. So what will happen at the high temperature? There will be a possibility of 3,3 sigma tropic rearrangement. So the reaction will go to the chair-like transition state, and this OH group should be in the equatorial position because due to the eliminate syn 1 diacetyl interaction, because other substituent is not there. So after 3 sigmatopic rearrangement, we get this product like this, and this is conjugated enol. Okay. So in and all means conjugated double bond and OH. That's why it will tautomerize to corresponding ketone because the ketone form is more stabilized form. So we'll get this product. But there is another thing is that if we somehow generate the carbon anion in this particular reaction using potassium hydride and 18 crown 6, so that time the reaction will be much more faster and we can perform that reaction at room temperature even in low temperature 0 degree centigrade, and the reaction time will be also less because this carbon anion will stabilize the transition state. That's why this type of reaction will go faster. And the 18 crowd is basically used to trap the potassium ion here. And that's why the reaction will be much more faster than the corresponding. If we use the potassium hydride, that time also reaction will be faster. But additionally, if we add the 18 crown 6, that time the reaction will be much more faster than this type of first example. Okay. So let's come to our question. So this is a alpha beta unsaturated ketone. So this is keto and this is alpha group here. This is beta group here. And the organolithium is in hard in. This is the hard electrophile. Okay, this is the hard electrophile. That's why the hard interaction will be good. That's why this reaction will happen whether it's in this position or this position, that we have to find out. So for that, this is our hard center. So this is our soft center. We all know that hard interaction is good and soft interaction is good. That's why our this thing, this nucleophile Li plus and this minus is in soft in nature. That's why our nucleophile will attack at this position because our nucleophile is hard in nature. Our nucleophile is hard in nature, that's why we'll attack this side and we will get the product like this. Because let's say we are assuming that this particular group is upside, so due to the steric, the nucleophile will come from the lower side, so that's why the oil group will go upside and this our particular nucleophile go in the downside. That's why we are getting the particular stereochemistry. So again, this oxycop rearrangement will happen. So the carbon ion will be corresponding form and the potassium will tap by the crown ether and we will get the product. So 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 this is our thing. So we can redraw this like this in the chair-like transition state. Okay, in the chair-like form. And this is our chair-like transition state. Okay. So what will happen? We have numbering again. 1, 2, 3. This is 1, 2, 3. So there will be a 3 sigmatropic rearrangement, right? This one will come here, this will go here, this will go here, right? So this is our transition state, and this transition state is the thing is that this is a trans-recurring system take transition state. That's why only one particular type of form is possible. Two type form is not possible if we know the trans-recurring system. And after that we'll get the product like this, and that will automatize here again the corresponding keto form, and so the methyl group and this CH2 group in the same side. That's why we get the product like this. Okay, so the stereochemistry is basically decided by this particular bond. See, this is the particular bond, and this bond and this methyl group. See, these two are in the same side. That's why we are getting the product. This CH2, basically this CH2 and this methyl group are in the same side. That's why we'll get the C stereochemistry here. Okay. So our product will be option A, not option C, because that is not possible. And similar reason here that there is no question of aromaticity because there is you're getting the more double bond, that is not possible. And this type of ring fragmentation is also not possible. That's why our right option is A. So for this type of video, you can watch this NPTEL video. Thank you. Okay, tell me, is there any question or not? Is it okay? Or
I have to explain one time. Tell me. It is difficult to understand. Okay, fine. Any other question? I think I hope this is also fine. Now the next question.
Hi everyone.
Now try to solve this question. This is easy question, I think. So this is the question from GATE 2019, and so this is our alphabet unsaturated ketone. We are using organocopper complex followed by phenyl selenium bromide. So the product will form something that is again treated with H2O2. So what product will form? So tell me the answer first. Try, then we'll solve. Another option. Please try. It may be wrong, no problem. Tell me. Okay. Except Ashish, anyone, please try. Okay, then solve it.
Now we discuss about one question from GATE 2019, question number 41. So in the following reaction sequence, the products P and Q are. So there is the one alpha beta unsaturated ketone. So and first we treat it with copper, methyl copper reagent, and then phenyl selenium bromide, and followed by hydrogen peroxide. So we have to find the product. So the first option is basically this selenium is attacking from the different phase with respect to option B, and option C is basically this methyl copper reagent are attacking from the same side, I mean from the keto position. So we have to find out which option is basically correct. So first, to know this type of organocopper reagent, we have to know the two things. So we can say this is alpha or beta, and this is beta with respect to keto. So keto group is here. So and there is a double bond. So we can bond this is alpha beta. So sometimes it is called alpha beta unsaturated ketone. Okay. So and we can numbering like this: 1, 2, 3, 4. We can numbering like this. So when the nucleophile is coming, they can attack in this 4 position,
or they can attack in two positions. That basically depend on several factors. So now we have to discuss. So first thing is that this center is hard in nature. Why this center is hard in nature? Because it is near to the oxygen. That's why this center is hard in nature. But this center is soft in nature because that is far apart from oxygen. So we all know that the hard interaction is good, soft interaction is good. If our nucleophile is soft in nature, then the attack will happen from the 4 position, and if our nucleophile is hard in nature, then the reaction will happen from the 2 position. So we have to find our nucleophile. What is our nucleophile? This is the Me minus, that is attached with the copper. So copper is soft in nature. So that's why this is soft in nature. That's why the attack will happen from this side. Okay. So we'll get the product like this. Okay. Let's assume, because this double bond is both the phase attack is equally feasible. That's why let's say methyl group attacking from the upside. So that's why we get this product. Now after that, another reaction will happen, that is with phenyl selenium bromide. In that case, this will be happening basically due to the one SN2 reaction. This oxygen will come like this, and this bond will attack here, and selenium and bromine will leave. So we'll get this product. Now we have to decide the stereochemistry. For deciding the stereochemistry, we can read out the structure like this. So if we numbering like this, 1, 2, 3, 4, 5, 6. So this is the half chair conformation. So we like H means half chair, and 5 inches upside and 6 in low side. That's why we call 5H6. And if we numbering like this from this oxygen, 1, 2, 3, 4, 5, 6, 7. So we can like this, that 6 is upside and 8 up there and 5. This is relative numbering. We can give any number, right? There is different convention, different substrate. So like if we numbering like this, then this is the 5H6, where 5 center is the upside, and in this case 6 center is the upside. So we have to find which center, which among these two are equivalent in nature. I mean, different type of conformation, and which conformation is more stable. This is more stable because this methyl group in pseudo-equatorial position, whereas this methyl group in pseudo-axial position. Due to the similar region, one triaxial interaction, this structure will be not stable, but this conformation is stable. That's why the reaction will proceed to this particular conformation, not this conformation. So that time, as the methyl group is upside, so the selenium will attack from the below face of the compound. So selenium, so our electrophile will come from the below of the face. So that's why like this and this one will come here. Electrophile will attack it. So our electrophile will come from the below of the face. That's why the methyl group in another side and phenyl selenium pH in different side. After that H2O2, this selenium center will be oxidized to the corresponding selenium oxide. Okay. After that, when we heat or anything, so in the room temperature also there is a possibility of syn elimination. So what happened basically, this oxygen will, this bond will come here, this will go, and this like go. Okay. So there is basically called syn elimination. I mean same site elimination. That's why this is called syn elimination. So we'll get a substituted alpha beta unsaturated ketone. So this is our product. Okay. So the correct option will be option number B, right? So in this case, this how this can attack is not possible, because that time one again tautomerism, then followed by this reaction. This reaction is normally not possible, not feasible. Okay, and this is 1,2 addition product, that is also not feasible because our
nucleophile is soft in nature. So correct option will be option B. So for more this type of video, you can watch this NPTEL. It is fine or not? Is it okay? Or I have to explain one more time? Okay, tell me, if you use CH3 MgBr, if we use like CH3 MgBr, what addition will happen? 1, 2 or 1, 4? This is hard or soft? If we instead of this, if we use this one, what will happen? I mean 1, 2 addition or 1, 4 addition? This is 1, this is 2, this is 3, this is 4. So this is 1, 4 addition and this is 1, 2 addition. So what will happen? In presence of methyl magnesium bromide, okay, 1, 2. Anyone think 1, 4? Okay, this is because this is hard in nature. Second, CH3Li, if you use CH3Li, what will happen? 1, 2 or 1, 4? CH3Li? No, CH3Li, Li is hard in nature, na? Because the all the element in the periodic table, like like hydrogen to say, I mean period one and period two, first, second, third row. I mean first and second row. That will be all in hard in nature. Like lithium, magnesium, they all will be hard in nature. Okay. If we use CH3Na, suppose that time both attack can be possible. I mean 1:1 attack. Here 1 2 attack. Here also 1 2 attack. But here both attack 1 2 and 1 4 equally feasible. CH3Na. Okay. If we use CH3 whole to Zn, then tell me Zn is hard or soft? In the case of Zn, Zn is soft in nature. Yes. So 1 4 addition. Okay. Achha, can you tell me what will be the NMR value of this organolithium compound? Suppose we are taking CH3 minus Li plus. What will be the delta value of this CH3 in 1H? And any rough guess. Normally CH3 come around 0.9. Normal CH3 group in around suppose R CH3. This CH3 come around 0.9. What will be value of CH3 minus Li plus?
Any rough guess. It will be greater than 0 or less than 0.9. Just tell me it will be greater than 0.9 or less than 0.9 in 1 h NMR. Delta value in 1 h NMR.
Greater than 0.9.
Why you are thinking it is greater than?
Excess of electrons may be shielding effect.
So shielding means less than less will be now value. So in the NMR scale, in the 0 to 10, this is more shielded, means more electron, right? And this is less deshielded, means less electron. So where the less electron will come, that is higher value. Where the more electron will come, that will be lower in value. So the value will be now less than 0.9, right? So its value normally 1.2 minus 1.2 ppm. This is below 0. Okay. So remember this thing. Sometimes they ask, you have done this reaction. After that, this 1 point minus 2 p is gone. So how can you monitor this reaction? This reaction is going on not. So you have to just take the NMR. If 0, this peak is gone, that means our reaction is done. Okay. Okay. Fine. Okay. One more question. Can you tell me? There is two center, right? Oxygen center have also negative charge, and this carbon center is also have attack is possible. Why that oxygen attack is not possible? C attack is happening here. No oxygen attack. I mean, why not OACPH? Why the attack is happening from carbon center? In this molecule, there is two center, right? In this molecule, there is two center. So two attack can be possible. Oxygen attack is also possible. This oxygen attack and this C attack is also possible. So why oxygen attack is not happening here? C attack is happening here. I mean, it is possible to attack with oxygen. Suppose here we are using phenyl selenium bromide. If we use P double bond O OET methyl methyl, that time what attack will be happen? Any idea? Okay, again same concept is come. Again carbon is soft in nature and oxygen is hard in nature. Okay, so again same concept. I am telling. So this oxygen center is hard in nature and this carbon center is soft in nature. Our selenium is soft, that's why soft interaction we are getting this product. But in this case, this PO bond is hard in nature. That time the oxygen will attack and that time we will get product like this. Here will be the methyl, here double bond, here O, then P double bond O, Me. It is okay, it is clear or not? Okay, fine. Now, another thing, another type of this type of scene elimination is also observed in this case. Like suppose if you have N Me2 and here if we have hydrogen and here something else, I don't care, R1, R2, R3. R4. That time if we also H2O2, that time N will be the N oxide, and similarly one syn type elimination is possible. Remember just this thing, just N in the case of NMe2. Okay, there will be in some alternative where this question will come. This one for addition and an elimination. So if we use selenium oxide, then also syn elimination, NMe2, that time also syn elimination. So we have to use H2O2. Okay. In some paper there will be H2O2 or PHCO3H. This is called par acid. Okay. This type of option will be there. In presence of H2O2, they will use par acid. So you have to know which type of oxidative type of reagent is available there. Okay. So they will just change that and they will frame one question in the next year. And every year this question will come. Okay. Can you tell me what is the driving force of this oxycorp reaction? Here two double bond is there. Here also two double bond. So what is the driving force of this reaction? Tell me, I am telling you that here is also two double bond. Here is also two double bond. What is the difference here? What is the difference here? Here both two are C double bond C. Two C double bond C bond. And here one is C double bond C and one is C double bond O. So the driving force is basically this stabilize C double bond O. So C double bond O is more stable than C double bond C. That's why this reaction is happening. So in when you will find in the exam that suppose this type of option like no reaction you cannot guess. That time always remember there will be one pericyclic reaction. Suppose if you give this reaction, just they will give potassium hydride. So what you will think? This oxygen minus will abstract the proton. Then you can think no option, right? That time always remember that is the pericyclic question. So you have to think that time 3 sigma topic rearrangement. This aldehyde reaction, this type of reaction is normally come and 2 3 sigma topic rearrangement. These three reactions normally come if this type of question is there. Okay, and you have to find the this relationships. I mean 1 2 3 and 1 2 in a disalder like this type of moiety. You have to find in the whole molecule. Okay, that is the thing. Okay, do you have any question? Any question? Okay, can you tell me how you differentiate between these two? Suppose they have frame one question. Suppose in the next year they suppose they give them same question and they write this is his product, right? And one is the trans product. How you differentiate these two? Whether our product is cis or trans using NMR? Using NMR, how will differentiate that our product is cis or trans? Do you people know car plus correlation? I am giving hints again. Okay, we are telling you what is the car plus correlation. So do you people know coupling constant like J, coupling constant? Okay, if you know, don't please watch that NPTEL video. Okay, in the NPTEL there is a one A 13, so they are nicely explained. Okay, so the coupling constant is basically, suppose we know CH3 CH2. What will show? This CH2 will show one triplet because n plus 1, right? And this will show one quartet if like this. What is this? So this will show triplet and this will show quartet. So the coupling constant is basically among these two how they are talking actually. What is the value of talking? The triplet, suppose triplet is 1 is to 2 is to 1. The gap between these two peaks, I mean these peaks and this peak is called the coupling constant. The significance of the coupling constant is that how they are talking, how much they are talking. If the coupling constant is high, that means they are talking very much. I mean, the speaking will be very much. Okay. So there is one scientist, Karplus, who gave one correlation based on the dihedral angle. Dihedral angle is basically, suppose, like we have shown now, this is the dihedral angle. Suppose this is our fixed angle. What is the dihedral angle between R and R here? In this case, tell me. What is the angle between these two? This is called a dihedral angle. For that, you have to first merge these two center. This center and this center, you have to come in the same direction. Then draw the angle. How much angle? This is 180-degree angle. Is it okay or not? This angle, this R and R, this is 180-degree angle. So they draw a correlation like this. Here the J value and here is the dihedral angle omega, and the curve is like this. This is for 0 degree, this is for 90 degree, this is for 180 degree. So at 0 degree J value will be less, at 90 J value will be 0, means no talking. If the angle between two hydrogen is 90 degree, that means there will be no talking. That time the coupling will be 0. I mean no splitting will be observed. And at the 180-degree angle, the value will be maximum with respect to 0 also. So in this case, the value is around 180 degree. And in this case, this is around 60 degree. 60, or we can say uh, 90 degree, around 90 degree. So here the coupling will be much more and here the coupling will be less. Okay, that is the thing. So here the J value will be around 12 to 16 and here the J value will be around 6 to 10 hertz. That's how they are confirmed. If they are trans in nature to hydrogen, then their coupling will be high. and there if the C is in nature, their coupling will be less. That is the Karplus correlation. So in the question they will give the J equal to 14 hertz, suppose. Then you have to understand that is trans bond. If they give J is equal to 8 hertz, then that is cis bond. Just you have to understand that. Okay. Is there any question? Okay. Is there any suggestion? Okay. Then we can stop today class. Thank you. Thanks for joining.